Hello everyone, my name is Atani Ruiz, and today I'm going to be presenting our work Protecting Against Image Translation Deepfakes by Leaking Universal Perturbations from Blackbox Neural Networks. This is joint work with Sarah Del Barjal and Stan Sklarov at Boston University. So first of all, I want to present this class of deepfakes called Image Translation Deepfakes, and this is an example architecture that uses only one input image and a class attribute input to change this input image, in this case changing the hair color of this person. This is animation that does a similar thing, except it changes expressions using action unit inputs. And this is a more modern variant of this image translation deepfake. Using only one input image, they can generate talking heads of this person. So we can see how impactful this can be in the real world and how malicious users of this technology can create misinformation, for example. So we want to defend against this. In previous work, we applied Whitebox Attacks to image translation networks in order to degrade and disrupt deepfake generation. In this case, we apply a fast grade inside method attack to the image on the left, and you can see that the attack is imperceptible and that the output of stargain is degraded as we increase the magnitude epsilon. In this work, we focus on Blackbox attacks because Whitebox attacks need the structure of the model and the weights of the model. In some cases, we only have query access to the model. So we're the first ones to present image translation Blackbox attacks. And our work also presents a more advanced version that is more efficient in these scenarios, in the image translation scenario, and we prove this in our experiment section. So this is the simple black box attack, Simba, on the classification scenario, where we modify one pixel in the input image in the positive or negative direction using a magnitude epsilon. And then, so now we have three images, the original image and these two modified images. We pass all of these through the classification model and we get the probabilities for the correct class Y. And we're just going to select the one of these three that has the lowest probability for the class Y, the correct class Y. So that way we're going to iteratively go and modify each pixel in the image this way. And then basically the output classification confidence for this class is going to decrease. We adapt this method to the image translation scenario. So in this case, we have an input image. We modify one pixel in the same way. And then we have this x plus and x minus, and we pass them through the image translation model. So now we have these output images. We're going to compare these output images to the input image with a metric L, and we're going to try to maximize this metric. Basically, it could be an L2 distance, for example, and what we're going to try to do is basically try to make this image as different as possible from this image. And this, in general, is going to increase the distortion in the output images. Okay, so now that we have black box attacks for the image translation scenario, we're going to present our leaking universal perturbations algorithm that it creates attacks that are more efficient and effective. So we have a leaking data set of images that has, maybe like 50 images, not too many. And we use this data set, we attack this data set using a black box attack. It could be the attack that we just presented or another black box attack. And we generate a set of perturbations P. This is the leaking phase of the attack. Now we're going to exploit this set of generated perturbations P. And how we do this is basically we generate a set of PCA components using this set of generated perturbations. And now we want to attack this target data set of images D. So instead of going pixel by pixel in the image using the image space basis, we're going to now use this basis that we've just generated. And what we're going to find in the experiment section is that the attacks are more efficient, and we can get attacks in as few as 10 queries for the model for a lot of our images in our target data set. And this is leaking universal perturbations, and this is the exploitation phase of our algorithm. On to results. Okay, so this first column is the original image. This second column is a modified, so the attacked image. So in the first row of this one, of these two examples, we're going to have the non-modified images. So these are the ground truth outputs of the star-GAN architecture for changing different attributes. So here we can see brown hair, blonde, brown here. Sorry, this is black hair. Same thing here. We can see blonde here, brown hair here. And the second lines, the second rows here are going to be the attacked images. So this image is attacked, this image is attacked, and these are attacked outputs. And you can see how the outputs are degraded. So these are unusable, and that's what we want. We want to protect the input image using a black box adversarial attack. So here are quantitative results, and we compare to our image translation Simba, and we compare that to our LUP algorithm that we present. And these are the number of queries required, and the height of the histogram bars means the number of images that are attacked using those amount of queries. So we can see that LUP, for a large part of the data set, these are 3,000 images here, only requires about 10 to 20 queries. And so LUP is very skewed to the left, which is very good, and much more than Simba. And these are the average queries necessary, and we can see that we have less average queries necessary for the whole data set. Same thing when we compare to image translation NES, or adaptation of NES for the image translation scenario. This is on star-GAN. The last one was on Ganimation. This is on star-GAN, and we have a similar finding here, where LUP is more skewed to the left, and the averages are better. Finally, some numerical results here. For Ganimation and star-GAN, we can see that LUP needs less average queries than its competitors, our adapted black box attacks that we present in the paper here. We also see that the success rate is very comparable and exactly the same for a lot of these, or even better. And the average norm is a little bit larger than some of these, but it's still reduced enough. And in the qualitative examples, we see that the attacks are not perceptible in the input images in general. Thank you very much.